Hi, this is a video for compiler design, COMP442 and 6421. This is for week 7. In this video, I'm going to explain assignment number 3. Now, first of all, let's see where you get this assignment. So here on week 7, you will see assignment number 3. The handout is here and the video is here. Now let's go and see what is inside of this handout. If you open the file, you'll see first this read. Let's go to this README file. So the statement is in this PDF file here. There is an LL1 grammar because as you know full well, assignment number 2 was not that trivial. So and part of what is not that trivial is transforming the LL1 grammar, which is very error prone. If you made some mistakes and you would not come up with a correct LL1 grammar, I'm giving you one in this one here so that you can at least fix your parser before you continue working on the rest of the project. If you don't have a correct LL1 grammar, it's going to be very difficult for you to move on. That's why I'm providing you with one here. The source files, these are exactly the same source files that you had for the assignment number 2. Here, these example files, as I will explain right away, you need to construct the abstract syntax tree. And one of the things you have to do is to output the AST into a file. These are some examples of this. Okay, so let's go to the handout. So this is due on March 6th, 8% of the grade. Now in this assignment, you have to construct an abstract syntax tree out of the parse by augmenting or complementing your parser with abstract or syntax directed translation, as I extensively explained in class. Okay. So so the document that you have to provide is in 3 sections. First of all, the attribute grammar that corresponds to your implementation. As I'm going to show this here. Let's go here. In the slide set 8.5, can get at it, yes. So in slide set 8.5, I present exactly what I'm expecting for you to have as an attribute grammar. So in this slide set, there is an LL1 version of the expressions for a grammar that is very similar to what we have in the project right now. So these are the rules of the grammar. So essentially what I want you to do is to come up with an attribute grammar by which you are inserting some symbols here that represent semantic actions. And these semantic actions are there to create the abstract syntax tree. So each of these semantic actions are essentially one step forward in the creation of the tree. So you need to figure out in what order these semantic actions need to appear in the processing of your grammar. So that's why I'm asking you to represent this procedure by an attribute grammar. Okay, so that's what you need to provide in this first part of the document. Okay. Second part, design. As usual, I'm asking you to, if you design new components to implement this, you have to describe them, describe how they relate to other components in your compiler, so on and so forth. Doesn't need to be very extensive. You need to have just a narrative and possibly a diagram describing what is the design. Same thing as for all the other assignments, also use of tools. If you use libraries to do your implementation, use some tools. For example, here I'm going to propose that you use the GraphViz tool. If you use that, then you should mention that there. So what do you need to do in terms of implementation to augment your parser with syntax-directed translation? Again, as I explained in class extensively. So, so what you need to do is to make it so that as the parse is happening, that you insert some code, pieces of code inside the operation of the parser, so that step by step it is actually constructing a tree, an abstract syntax tree. Very important to understand. Often, unfortunately, some people would make a mistake of creating a tree, which is in fact a parse tree. So it is a tree data structure, but unfortunately, a mistake is that it's a parse tree, not an abstract syntax tree. So I've explained in class extensively what's the difference between the two. Make sure that what you do is an abstract syntax tree and not a parse tree. Eventually, this parse tree, this abstract syntax tree is going to be what we use in phases 4 and 5 to actually do the semantic checking and the code generation phases. So in fact, this AST is an intermediate representation that is somehow the hinge between the front end, which is the parser and the lexical analyzer, and the back end, which is the semantic analyzer and the code generator. Now, in order to be able for us to verify that your tree is correct, I want you to output the tree in some kind of text form into a file so that we can look at this file, the markers can look at this file and see if the tree actually corresponds to the program that you parsed. Now, there are different formats that you can use to do that. Let's go and see the examples that I gave. So if you go to examples here, okay, first of all, it's important to understand, so this is the source. So source that I'm giving here, it's not exactly the same language that we use now. Okay, so even if you try to compile this, it's not the right language, just giving you that as an example. In this case, of course, it's very similar, but it's not exactly the same. So this is a function definition, and then here you have your program function, which is essentially the main function of this program. And each of these have parameter declarations. Some of these are arrays, variable declarations, and then statements. Okay. Now, this is this particular program. Now, you can actually output the AST into a file, which might look like something like this. Oops, no, wrong thing. Open with. Okay, so you could output like something very simple like this, where, for example, this is your top prog node, and there's class list, which is here, and then you have a class declaration and so on and so forth. Okay. Then you can also use the dot language. So, for example, for those of you who know that, GraphViz dot is very popular tool that you can use to actually represent a tree. So that is, for example, what it looks like. Okay, so this is in fact a text file. If you open it with Notepad, you see that this is a text file. Okay. So that's why I give you the example. You will see, of course, it's easier to do the text representation as I shown you before, but it's actually not that difficult to generate a dot file. You have two choices here. Either you generate this file as the whole process is going, or you generate the tree and then you create an algorithm that later traverses the tree and then generates the file. Okay, you might find that it's actually easier to get the tree and then traverse the tree to generate the file. Okay, so I'll let you figure out which one you prefer. So all this to say that I want you to output the tree, the AST, to a file. You have a choice between these two kinds of formats. Let's go back to this. So that's the output. Of course, you need to provide your own test cases. I would suggest that you use the same test cases that you had for assignment number 2. There's no difference between the test cases here. It's basically to cover all the syntactical constructs of the language. Okay. So you could reuse, in this case, your test cases that you had for assignment number 2. And of course, provide a driver that the marker can use and that you would use actually to drive your demonstration. So that's about it for that. So here's the grading scheme. I'm going to provide you later on with a detailed grading scheme that corresponds to this. So that's it for this presentation. Thank you.